The topic is Prim's algorithm. It is also the algorithm for finding the minimum spanning tree, just like Kruskal algorithms. Both Kruskal and Prim's algorithms are greedy approaches. Now, how to start with this algorithm? For Prim's algorithm, you will have to start randomly from any of the vertex. Say we are starting with the vertex A. Now, I am right now creating one more set, which is additional set, which will keep track of the vertices which I am taking into account for creation of minimum spanning tree. So this vertex A, if you consider see it from where we are starting, this will be part of that set say T. Now we have to first find all the edges which are emanating or originating from these set of vertices which are there in the set T. Now set T contain only the vertex A. The uh, outcoming edges or the edges emanating from the vertex A are AF, AD and AB. Remember that we have to only consider the direct edges. Now out of these three edges, if you consider the weight of these, the weight of this is 2, 17 and 16. We have to pick the minimum weight edge. So minimum weight edge is AB. So that next vertex which will be chosen according to this will be AB. Now once AB has been chosen, make this B as a part of this partial set T. Now AB is being chosen. Now again the method is being applied. Now this set means that set T contains the vertex AB and there is one remaining set which is not a remaining partition which is not a part of the set T. These are the set of vertices. Now out of these set TAB, find the edges which are coming out directly from these set of vertices. The edges are AB, AF, AD, then BD and BC. Now, if you consider this case A to F, if you consider the vertex F, only the direct edges from this partition, if you just see the red color partition, only the direct edges from A to F. The remaining that edge cost is 16. We'll consider this edge. Now coming to the vertex D, which is outside this partition containing from the set T, this D vertex has got two edges coming out from this partition, A to D and another is B to D. Now which edge you have to consider for your purpose? The minimum cost edge, which is going from this part, which is connecting D to this partitioning containing two elements. So D is being connected to this internal partition with set T with the minimum cost edge you have to pick is 5, not 17. To 17 won't be picked, 5 will be picked here. Now coming to the edge C, which is directly connected to B, only one edge is emanating coming out from B, that is B to C, 15. So out that means the edges for consideration will be 16, 5 and 15. Get the minimum out of that. The minimum out of this is 5. So we will picking the edge BD, which is having minimum cost edge, that is 5. Now the partial set T will have three vertices A, B and D. Now this A, B, D, this set will disconnect this, will separate this graph into two partitions. One containing vertices A, B, D, another partition containing the remaining set of vertices. Now moving further, this set of vertices A, B, D, now considering this partition, just you can draw this partition between the vertices containing A, B, D and remaining vertices. In this partition, if you carefully scan, for the vertex F, there are possible edges which are going to this partition containing ABD. There are two edges. One is edge AF, another is edge DF. We have to pick the minimum cost edge out of this. Minimum cost edge is 16 or 9. Minimum cost edge is 9. So we'll be picking this green color tick, that is 9 edge, that is DF edge. Now coming to the vertex which is directly connected is E vertex. The E vertex is being connected directly only to this partition through the edge DE. The edge weight of this will be 8. Now coming to the vertex C, C is connected to this partitioning containing ABD through two edges. Those two edges are B to C and D to C, but we'll be picking the minimum cost edge. Out of 15 and 13, the minimum cost edge is 13. So 13 is picked here. So out of this possible set of edges which is going out from this partition containing A, B, D and remaining vertices is only 9, 8 and 13. Picking the smallest one, that is from D to E, you got this answer. Now from this onward, what you will be doing again, generate the partition like this. That means now this partition contains the vertices A, B, D, E, and the other partition contains remaining set of vertices. Now going to remaining set of vertices, if you consider the vertex F, F has got two edges going to the partition, that is F A to F, D to F, and E to F. Out of these three edges, the weight of the edge which is minimum is D to F, that is 9. So ninth edge will be considered here. Similarly, going to the vertex G, now there is just single edge which is going to this partition from G to the partition containing T set of elements, that is E. So this 9 GE will be considered, edge will be considered as such. Going to H, only one edge is there, that is EH, that will be considered, that is with the value edge weight 10. Going to the vertex C, the possible vertices are edges are B to C, which is for connecting C to this partition, B to C, then B to C to D, then C to E. Out of these three edges, the edge with minimal weight is 11. So we'll be picking 11. So the considered edges will be having the weight 9, again 9, then 10 and 11. You can pick any of the 9 because 9 is the minimum. You can pick either this edge or this. Say for the sake of convenience, we are picking the edge DF. So this is the partial answer. Now the set will have the values A, B, D, E and F. Now again draw the partition of the same. Now again considering the vertices outside this partition, let the vertex, now considering the vertex G. Now G has got two connections with this partition. One is GF, another is GE. If you carefully scan, so out of GF and GE, the minimum cost partition is 4, that is GFH. If you consider the vertex H and connectivity of this vertex H to this partition shown in violet color line, if you consider inside this boundary of red color, then the considered edge is only one, that is E to H, so which is having the cost of 10. So this edge will be considered for the purpose. Now for C, the possible edges are which are going through this partition are this is BC, that is 15, then CD 13, then CE 11. So out of these three edges, 11 is minimum, so we will considering 11. So that means for the purpose of finding the MST, we will considering at this iteration the edges with cost, that is GE with cost 4, then EH with cost 10, then EC with cost 11. Out of these three cost, this GF edge has got minimum cost, the GF will be considered further in the next iteration. Now the set of vertices which now will be involving G also in the final set. Now again creating the partition having this set of T vertices and the remaining vertices. So this partition, now if you consider the vertex for H, for vertex H there are two possible edges which are connecting this H to this T set of partitions. One is HE, another is HG. So out of these two, 10 is the minimum cost edge, so we will be considering this edge for our purpose. Now considering the vertex C, the possible edges which are connecting this C to the partition the vertices, that is of T vertices, set of vertices are C to B, that is 15, C to D 13, C to E 11, and that's all. Out of this 15, 13, 11, 11 is of minimum, you're considering this 11. Now that means the edges under consideration are 10, 11. Out of this minimum is 10, we're picking the minimum as this one. Now after this, your set contains A, B, D, E, F, G and H set of elements in the set T, temporary set T. Now the remaining vertex which is being used for this partition will become this one. Now this vertex will have possible connection with the set of partition is BC15, CD13, CE11, CH5. Out of these, when the minimum edge cost is that of 5, we'll be picking the edge CH for our purpose. This is the final output of minimum spanning tree using Prim's algorithm. If you want to find the cost of this, find the sum of the edge weight cost of violet labeled edges. So if you can just stop wherever you want, that is if there are n vertices, once you get n minus 1 edges in your iteration after some set of iteration, you should stop there only because we got the answer. In minimum spanning tree, there are always n minus 1 edges for given set of n vertices. If you want to find the cost of the minimum spanning tree, you just find the sum of all these edge weights, you will get the cost of this minimum spanning tree. Let us take another example. Let us suppose we want to find the minimum spanning tree for this given graph. For example, we are starting from the vertex say B. Now B is a part of this partial set T, and B edges originating from B are 4, 11 and 8, and smallest weight edge is AB. So we'll be picking the edge AB in this case. So AB is chosen. After this, the set now contains A and B both vertices in one partition, and remaining partition contains remaining set of vertices. The emanating edge from this are AH, BH, and BC. Now considering this from AH, BH and BC, if you consider this vertex, there are two possible connections from this vertex is 8 and 11. The minimum cost edge to go to edge from this partition is only 8. So we will be picking 8 out of this. So considering direct edge from this B to C, that is 8, that is the only edge, so we will be considering this edge as such. So the possible edges for consideration are 8, 8. Now you can go in either direction, either you can go for AH or BC. Let us suppose you have chosen BC for your purpose. Now in this case BC, again draw the partitions so the same, containing the one partition containing the vertices A, B, C, another containing rest of the vertices. If you carefully scan for the vertex H, the possible edges for consideration are 8 and 11, and we will choosing picking A for our purpose being a minimum cost edge. Next comes for the vertex say C. For vertex C, again for the vertex I, not for the vertex C, for the vertex, because C is a part of this, already a part of this partition, we will have to consider the vertex I, which is in direct connection with the partition. Now vertex I has got a distance of 2, direct distance of 2. This will be one edge which will be for consideration. Similarly, another edge for consideration will be CF, that is 4, which is going through this partition. Next will be CD, which will be involved in the process of finding the minimum cost edge. So these are the 4 edges which will be involved. Out of these 4 edges, minimum cost edge will be of that of value of 2. So CI will be considered further. And now the partition will be containing, one partition will be containing A, B, C and I, and the remaining partition will be considering remaining set of vertices. Out of these set of vertices, if you consider for edge, the possible edges which are being going from edge to this partition on the other side of the red color, that is 8, 11 and 7. So the minimum cost edge is 7. We're picking this edge for our purpose. Similarly, if you consider for the vertex G, the only edge which is connecting this G directly with this partition is GI, that is of 6. Similarly for F, the direct edge for that is CF, that is 4. For D, the direct edge is 7. So we're considering these edges for our purpose and finding the minimum out of this. Minimum out of this is CF edge. The CF edge will be considered further. The F will be added into the final result of partitions. So A, B, C, I and F. So this F is being added. Now after this again redraw the partition. The partition drawn will be this one. Out of these again, if you consider edge, the considered vertex edge will be 7 because it is the minimum cost edge. Then comes your vertex G. G will have options like 6 and 2. Out of 6 and 2, minimum cost edge will be 2. So 2 will be picked here. For D, the two options are 7 and 14. So 7 will be picked out of this. For E, the only option is 10. So those very vertices edges will be chosen by the algorithm. Out of these but edges, the minimum cost edge is GF, that is of value 2. So GF is being chosen. After this, again redraw the partition. Now the partition will also contain the vertex G along with the previous set of values, vertices. Now once you're creating a partition, now considering the case of H vertex which is outside this partition, the possible edges which are connecting this edge to this partial partition is 11, 8, 11, 7 and 1. So 1 is the minimum cost edge, so we'll be picking 1 for our consideration. Now the remaining other vertices are F, E. E has just got the one direct connection, so 10 will be picked out of this. 10, that is EFH. Now D has got two connections, 7 and 14. 7 will be picked out of this. So these are three edges which will be considered for our purpose. Out of these three edges, the minimum cost edge is HG. So one will be picked like this. So H will be a part of now this partial partition. So this is the now remaining vertices out of this are, now redraw the partition. Remaining vertices in this are D and E. If you carefully scan, E is directly only connected to this partition through the direct edge, that is of value 10, that is EFH. D is connected to this partition through two edges, that is 7 and 14. The 7 will be picked out of this. 7 and 10, the minimum cost edge is 7, that is CD edge, which will be a part of the minimum spanning tree. So C is being calculated, used. That means D will be a part of now this partial partition. The only thing which is remaining now is the edge, that vertex E. And if you redraw the partition containing these violet color edges along these vertices and separating it from the separator, the possible distance of E from these edges is minimum distances out of 9 and 10 is 9. So we're considering 9 only one vertex is remaining, so we'll pick this 9 as such. This is the result of the final minimum spanning tree, which is being shaded in the violet color. So this is starting when the starting vertex is B. So if you want to find the cost of minimum spanning tree, find the sum of all those violet color edges. You'll get the cost, that is the minimum cost of the spanning tree using Prim's algorithm.